Hi, my name is Paul Lamar, and I'm with Gordon Anderson from Mistral, and he's going to tell you a little bit about the Mistral rotary engine designed for Cessnas and Pipers and so forth and so on. Has certain advantages. So I'll turn it over to Gordon here.
Hello, my name is Gordon Anderson. I'm Chief Engineer, Chief Operating Officer of Mistral Engines. The origin of our project goes back to the mid-90s when a Swiss aircraft and aircraft engine maintenance facility decided to look for a more appropriate technology for modern general aviation aircraft. They had a very long and in-depth background with both Continental and Lycoming engines and started a review of modern engine technology and its applicability to an aviation environment. They reviewed turbo diesel engines, standard reciprocating engines, and finally settled on the rotary engine technology as being the most promising in terms of the reliability, maintainability, and operating cost advantages that it offers. Mistral Engines was set up in 2001 as a company to take on the project full-time and to develop the engine towards a commercial product. Let me take you through the fundamental advantages of a rotary engine for aviation use. First of all, we have the issues of fuel availability and environmental concerns today. The rotary engines are very well suited to a multitude of fuels, gasoline of various qualities, automotive qualities with ethanol blends, or aviation fuel, Avgas 100LL. The rotary engine will accept all of these fuels with no problems at all. The second advantage of the rotary engine, not exclusive to rotary engines, but liquid cooling, eliminates the problems associated with thermal shock on air-cooled engines associated with reduction in power and rapid descents. The liquid cooling will keep the engine at a constant temperature, irrelevant of the power level and the flight speed. It also helps the engine to warm up quickly and leads to more stabilized temperatures within the engine block, which assist to extend the TBO, the lifetime of the components. The rotary engine has very few moving parts, approximately 90% fewer moving parts than a reciprocating engine. The motion inside the engine is entirely rotational, so there are no unbalanced forces within the engine, meaning also that you have a very low vibration, and that assists a lot in extending the lifetime not only of the engine but also of the airframe and the avionics. We've also chosen a low propeller speed for the Mistral engines, 2,250 RPM for takeoff and 2,000 RPM for cruise. That results in a net reduction of engine noise or power plant noise of 10 decibels, which is 70% less noise. And the form of the rotary engine basically allows a very streamlined cowl to be built around the engine, and is also a fundamental advantage of the rotary engine vis-a-vis a conventional air-cooled boxer engine. So we're looking here at a G200 engine. This was one of the first developments of the company. Originally, the prototype engines were based on a Mazda 13B engine block from the RX-7 car. That's this section of the engine in here. Mistral Engines developed a planetary speed reduction unit for the propeller and the installation at the back of the engine to integrate structurally into the aircraft and to carry the accessories such as water pump and oil pump, which are required for the aircraft installation. We have the intake system over the top of the engine, and at the rear of the engine we have the rear plate and accessories drives. This is the part which integrates the engine into the aircraft through these 4 attachment points. We have the water pump here, the oil injection pump here, the oil filter, and the primary alternator, which is used for powering the FADEC system and the electric fuel pumps. This is the G230 TS engine, which in all aspects, or most aspects, is identical to the G200 engine, but obviously has the turbocharger directly bolted onto the engine block. The performance of this turbocharger gives us a critical altitude of 18,000 feet, where we have the same performance as at sea level, and provides us 75% power at up to 23,000 feet altitude. So we're looking here at the mock-up installation of a G300 300 horsepower engine, naturally aspirated, in a common four-seat aircraft. We show here the coolers underneath the engine. Could in this case be fed by a chin inlet underneath the propeller. The exhaust, this is a Mistral proprietary design. It's a dual skin system with a cold structural envelope, and the inside parts are made from a high quality, high temperature alloy, Inconel 625. This protects the environment from the high temperatures of the rotary engine exhaust. We have the fuel system here. We have a fuel pressure regulator block which is mounted on the firewall with pressure sensors, temperature sensors, and a pressure regulator. And this is the box which encloses the 6 fuel injectors for this engine. The fuel injection system is unique. Mistral engines is the only aircraft engine which has dual fuel injection per cylinder. We also obviously have dual ignition per cylinder. That's standard in aviation. Looking at the right-hand side of the engine, we see the full authority digital engine control, the FADEC system. We have 2 engine control units, or ECUs, each fully independent. Each one of those ECUs is capable of running the engine on its own. So one of the prime concerns for us was certifiability of this engine and installation design. So we have redundancy throughout the engine management system, not only with the twin ignition per cylinder, the twin fuel injection per cylinder, also on every critical sensor on the engine, the manifold pressure sensors, we in fact have 3 sensors, and on the rear of the engine we have 2 RPM sensors, 2 oil pressure sensors. All of the important sensors are duplicated, so if one of them fails or gives a wrong signal, the engine will continue to run with very low loss of power. One of the curiosities of the rotary engine is that the sealing of oil between the eccentric shaft and the combustion chambers is so good that an additional oil supply is required to lubricate the seals on the apexes of the rotor. So this engine has an electronic controlled metering pump mounted on the rear plate of the engine, and 6 oil injectors, 2 for each cylinder, along the top of the engine. These white lines here are used to feed a small quantity of air to the oil injectors to get a good distribution of the oil within the cylinders. One of the advantages of having this metering pump is that the oil in the sump remains very clean, and the oil consumption is very well controlled in the engine. That means that we can in fact avoid the regular oil change which is standard for a reciprocating engine, because all we need to do is fill in the oil to keep the oil level controlled in the oil sump, and when it comes to the 100-hour service interval, exchange the oil filter but not exchange the oil in the sump because it remains clean.